So one of the advantages of doing quantitative social science is that it allows you to build bridges with different disciplines. So people from maths and stats, from engineering, from physics, engineering, they're all people that over the years that I've done projects with, and one of the things that the kind of common language is often statistics and statistical analysis. And in a world that's moving increasingly towards interdisciplinary research, particularly within academia, so I don't know if you're aware, but the research councils are all being merged together into one kind of giant institution, which means that's paving the way for ever more interdisciplinary research. If you want to be involved in projects and bidding for grants in the future, being able to work across disciplines is a really important thing to do, and a very rewarding thing to do. So if you think, I'm not ever going to be a statistician, that's okay. I'm never going to be a statistician, but I've learned enough stats to be able to talk to proper statisticians, like Nema, who's come down from Glasgow today to talk to us about social network analysis, and I'll hand you over to Dr. Nema Dean.
Thank you very much, Gwilym. So I think that's the first time in my life I've ever been called proper. I'm also the token representative of the north of the border from Scotland. I'm down from Glasgow, as it says at the top of the slide. And I'm going a little bit off the reservation compared to Todd and Andy, in that I'm not going to claim this method is going to be so useful to all of you all the time. It's vital. But if you're doing a particular type of research, this is going to be the only method that you should be using. So when you hear me talk about this, think about what your question of interest is and whether or not that lines up with this, in which case you should only be thinking about this. So social network analysis, there's a ton of different terms for it because it's come up in loads of different disciplines. It's come up in computer science, it's come up in maths, so it's known as statistical analysis of networks, it's known as graph analysis. There's a ton of different terms out there. So if you see graph or network in some sort of methodology, it's probably talking about this. And so to try and describe what it is, the definition given is methodological analysis of social networks, which doesn't really tell you very much. And basically the idea is you have connections between individuals and you're trying to look at the relationships between those individuals. So you're not actually necessarily interested in each of the objects that you're looking at, you're interested in the relationships between those objects. And so any network that you can define, you have little dots, which are your nodes, essentially. And then you have connections between them. So, for example, we might have connections between all these three, and then just one connection between those two. And that would define a network. And so these nodes, these circles might represent people, they might represent companies, they might represent countries, then they might represent academic disciplines, they could be anything basically. All we're interested in is, can we draw connections between them? And so here, a line connecting two of these indicates that there's a link between them, that there's a relationship there. And so if these are countries, maybe this is, France and Germany. So France and Germany had been at war together, so there was a link. And this one is, let's say, Brazil. Germany and Brazil have not been at war, so there's no link between those. And so we're not necessarily interested in investigating each of the countries. We might be interested in investigating, well, what are the characteristics of countries that draw us to have these connections, these wars or not wars. And so the idea is, compared to regression where you have an object and you have characteristics on that object, you talked about relationships between the characteristics that are still measured within the objects. Here, we're very much not caring about the objects themselves, but caring about the connections between the objects. And so we can still have information about these. If these are countries, we might have information about GDP or language used or so on, anything. And that might still be interesting and useful for predicting whether or not there will be links between countries. But the emphasis isn't on the countries or the nodes themselves, the emphasis is on whether or not there are connections between them. So, just to bring that back, we're not really interested in objects. And so, in sort of regular statistical analysis, which you're used to, you have sort of objects which you measure characteristics on. You might have means of those characteristics, you might have standard deviations over the sort of summaries that you get. And you might be interested in linear regression, which takes each object and says, okay, for this set of characteristics, can I predict the value of the other characteristic on this object? Whereas social network analysis is looking at relationship between objects. So we've still got the idea of prediction, we've still got the idea of summaries, but those take very different forms in this type of analysis than it does in sort of standard statistical or classical statistical methods. Okay, so when you think of social network analysis, instantly pop to sort of Facebook or Twitter or so on. And those are definitely examples of networks where we're interested in analysing, but they're only a very sort of specific example. And so it's any sort of set of relationships between objects or individuals or actors. And so there's a ton of different methodologies, and this sort of falls under the term of social network analysis. And so, like I said, it's come about in a ton of different disciplines. As I said before, you can think about conflict, so whether or not there are conflicts between countries. You could have talked about the relationship between countries in terms of trade, for example. Do I export a large amount to one country? Do I import from a country? Anything you can define between a pair of objects that is essentially connecting them or not is essentially then defining a network across a set of these objects. So, again, it's coming out, a lot of the methodology is growing from the sort of mathematical theory, and that was based on the idea of graph theory. So you'll see networks borrowing a lot of terminology from maths and their graph terminology there. So these sort of objects of study are called nodes or vertices or actors, and the connections between them are often referred to as edges or ties. And so instead of looking at each individual object as our mode of analysis, we're actually looking at pairs of objects. Those are the things we're interested in. The most common type of network that we look at is the simplest one. Is there a relationship or not? So yes or no, binary. So but here there's no relationship, so it would be 0. Between these two, there is a relationship, so we'd have a 1. And so that's probably the most common form of network that exists, and there's an awful lot of well-developed methodologies for that type of network. Now, obviously, you can have different types of networks. If we were talking about, for example, trade, we could be talking about these connections being the amount of trade between these countries. And so a thicker line might indicate a larger amount of trade. Here we have no trade, here we have some trade, and here we have most trade. So you can have weights on these things as well. So those can be counts, and they can be also things like multinomial variables. So there's the same sort of types of variables for connections as you have for regular variables on objects. But the methodologies, obviously, that you use to analyze these things are going to be different. So the most well-developed ones tend to be for binary variables, where you either have a relationship or you don't have a relationship. And quite often with things where you have a continuum, you can often dichotomize these to create a network which is binary, even if it wasn't initially so. And so you can have also different networks defined on the same set of nodes. So here we could have countries. We could be defining on whether or not they've had trade relationships, on whether or not they've had country conflicts, on whether or not there's migration. Same set of nodes, entirely different networks coming out of different relationships that you're studying. And you can analyze these separately and also multivariately. We can also talk about directions. So if we were talking about, for example, conflict, and my relationship was, does a country invade another country? So, for example, we could have Germany and France, and so we could say, Germany in the last 100 years has invaded France, but France hasn't invaded Germany. So this is what's known as a directed edge, so we go from one to the other, and not necessarily back. So here, if we have, for example, England and Scotland, over history, we've definitely had England invading Scotland, and we've also had some people making raids down to England as well. So this is an example of a directed tie where it's reciprocated. So directed ties obviously give us more information, but there's still a good deal of information to be had in the undirected ties, whether or not you have a relationship. Regardless of what type of edge you're looking at, you're always, again, looking at pairs of nodes as your object of analysis, and those are generally known as dyads. So the obvious thing to do when you have a network is visualize it. It's the easiest way of interpreting these things. It's pretty easy to understand. You put something up, you say these things are countries, this represents connections between them. It's very easy for anyone in your discipline to understand what's represented by that. The issue that comes about with that is, obviously, if you have a large number of nodes, for example, if you looked at all possible Facebook accounts and tried to draw that graph, you'd run out of ink fairly quickly, and it wouldn't tell you very much even if you could plot it. So we also want ways of representing this information numerically, because then we can analyze it using statistical methodology. So the way we do that is essentially using a matrix, which has the same number of rows as it has columns. So each row and column represents a particular node or actor. So let's say here we have 4 nodes. So we have a sociomatrix that represents this graph with 4 rows and 4 columns. And usually we have zeros along the diagonal because we say no node is essentially connected to itself. So here we have no connection between A and B, so both of those are 0. We do have a connection between A and C, so those entries are 1. We have no connection between A and D, so those are 0. Between C and B we have a connection. Between B and D we have a connection. And finally between C and D we have a connection. So I'm representing the same network information here as here. So it's fairly simple to do. For undirected, or for directed ties, this might not necessarily be a symmetric relationship. So here we have G and F. And so again, we have a relationship from G to F, but not from F to G, for example. So here the rows indicate where you start, and the columns indicate where you finish. So there is an arrow going from G to F, but there isn't one from going from F to G. And so when you have an asymmetric sociomatrix, that indicates that you have directed ties. So that's usually then what we're using to analyze. And so obviously as the number of nodes increases, these matrices get pretty large. So if we've got 10,000 of these, obviously you couldn't write it down on a page. And it can get difficult to actually store it, but there are some sort of efficient ways of storing these 0-1 matrices in computers now, so that's possible to quite a high degree. Okay, so I said it's very different analysis from your classical statistical analysis, but you still have the same idea. You want some summaries that tell you something about the characteristics of these things. And so you can talk about characteristics that are measured on the whole graph. You can talk about the characteristics that are measured at each of the nodes. You can talk about characteristics that are measured on the edges and so on. So this is like a very small selection of the ideas that we can think about. And so degree is basically saying how many connections do I have? So you can just count the number of edges there are. You could also say, well, how many connections do I have compared to how many I could have? For example, I'm missing a connection between A and D and A and B here. So I could represent that as a proportion. How many edges do I see versus how many edges could I potentially see for that number of nodes? Centrality is the idea of some nodes being more important than others. For example, A is not really very important here. It's only got 1 connection. Whereas B, C, and D each have 2 connections, so they're reasonably central. So centrality describes how important, in some sense, a node is. And connectivity is the same idea. How connected is the graph? So I could potentially have a further 2 nodes out here, E and F, which are connected but not connected to the other parts. So how connected the graph is an idea of how well you can get from any one node to any other node. So here, this graph isn't completely connected. It splits into 2 connected components. The idea of transitivity is, again, a sort of the friend of my friend is my friend. So if I have a connection between B and C and C and D, then I expect there to be a connection between B and D. But that doesn't always necessarily follow. So it's interesting to study that because it tells us something about how these edges form. We can talk about partitioning and I can never say that word the first time, right? Sortativity and mixing, which I'm going to mention in the context of an example in a couple of minutes. Just checking how I'm doing for time. Okay, so here's just an example of these sorts of relationships you can define just on individuals. So you can see that there's a large set of ways in which you can think about constructing networks on people or objects. Interesting examples that I've been involved with is the idea of HIV transmission. And here you have surveys of people and you ask them how they're connected. So you could have, again, multiple ways of defining a network on a set of individual drug users, whether or not they have unprotected sex between different pairs, or whether or not they share needles. And so it was of interest to look at that because we could identify the most central people. And those are the people who you want to, potentially provide prophylaxis to, or give access to needles and so on, and who can disseminate that sort of behavior and information, who are influential in some way. Similar idea for international relations network. We have countries or nodes. Edges can be number of interactions. And so it tells us something about, conflicts can arise not necessarily because you have, raiding parties or anything like that. It could be as the number of interactions starts to slow down or decrease. That could be a sign of tensions rising between different actors. And again, the classical example, Facebook, where you have the nodes are accounts and the edges are just whether or not those particular accounts are friends. And so this is a very tiny, tiny subsample of a Facebook network. But it's interesting to see because you can see that it is completely connected, but there are sort of regions of the network where they're very highly connected, but not necessarily connected to other regions. And so describing how these patterns comes about tells us a little something about the sort of social dynamics that are going on with these individuals. Okay, another example. It's fun. This, by the way, is based on the books, and it's only running up to the, what was it, the Storm of Swords? But it's basically trying to say, okay, based on how many people talk to each other, how important are some of these actors up to that stage of the books? And so you can sort of see Daenerys getting important. Tyrion was hugely important at that stage. And people have used this stuff to try and predict who's going to die in the next season of Game of Thrones. So if you want to, there's data out there. It's fun. It's a fun exercise to see if you can work out before you actually see the next season. You've got a whole year to work it out if you want to try it this time around. Okay, so just to give you an example to run through in the last 5 minutes. Yeah, my examples have a theme. So we have Grey's Anatomy. Assume you've heard of it? Yeah, okay. It's been around along. There's basically a lot of hooking up going on, and we were interested in seeing the patterns of those hookups. So this is kind of old data at this stage. It was 2011, but hopefully you'll still recognize some names. So here we go. We have 30 actors. And the links between pairs of actors are instances of them hooking up. They may not have a long-term relationship, but it happened at least once. And so the first thing you can see is it's not a completely connected network. There's definitely one big blob of very busy people on one side, and then some smaller, more exclusive sets on the left. And so the question is, if there's another outbreak of STIs, which individual would you target to try and sort of maybe give counseling to or provide a free box of condoms or something? So it wouldn't necessarily be any of the individuals on the left-hand side. It would be someone who has a lot of connectivity with the rest of the graph, right? And so someone like, say, actor 5 or, yep, exactly, actor 8, actor 20, 18, so on. So if you want to see the names, they're exactly who you think. So right in there is Karev, who might be your most influential individual in this network. So, yeah. Like I said, this is 2011. There's been a lot more action happening since then that has not been fully captured. So, this doesn't tell us very much. All the nodes are the same size. It doesn't give us a sort of visual information about which ones are really important. So what I've done now is given the size of the node is proportional to the degree of that node. So how many connections does it have? So it really pulls out who are the important individuals in this hookup network. So unsurprisingly, Karev is right up there. Is he a little bit more surprising? O'Malley, again, I wouldn't have picked him. And Grey, since it's her shows, I suppose has to be up there. So, but degree doesn't necessarily tell you everything. Yes, they've hooked up a lot, but maybe they don't connect different parts of the network, right? So we might want to talk about something like closeness. How close is one person to every other person in the graph? So basically, it means, how many hookups do you have to go to before you go? This isn't the most PC of talks, I'll give you that. So again, if we do this again, I've taken the names away to sort of spare embarrassment and sort of color-coded this. You can see they're probably the same people coming up here again. But we can also think about things like betweenness, right? If I have one particular person, if I take them away, do I split up the graph? So maybe that's more important than how many people they actually connect with. And so if we color code that, you see a number of different people who are suddenly more important, because if I take, say, this person away, even though it hasn't got a very high number of connections, it splits these people off. And so in terms of color coding, that's almost as important as some of the ones that have very high numbers of connections. So this is just sort of visualizations. It still tells you a lot about what's going on. And if we took a slightly less silly example, and these were countries, and interactions between countries, this might actually have more meaning. And I'm running out of time, so I'll sort of say a little bit. You can do things like clustering on graphs, so basically seeing which sets of individuals tend to interact more with each other rather than other people. And I'll skip sort of quickly over that. This sort of gives an example of how that looks on this graph. That's sort of all summaries, so like means and standard deviations that you connect with sort of standard classical analysis. For the sort of idea of linear regression, you have an extension in social network analysis that does the same thing, tries to predict whether or not there'll be a relationship between a pair of nodes. And so those models are known as exponential random graph models. And so they're just basically, if you've heard about generalized linear models, they're sort of an extension beyond that. And so they do the same thing. They try and say, given this set of characteristics of either the graph or of the nodes, how likely do we think there's going to be a connection between those two? So I'm just going to skip forward because I've, as usual, produced way more material than I needed. But anyway, mathematical equations that you don't have to worry too much about, but you interpret them similar to how you would with logistic regression, basically. Another idea that was sort of interesting that actually connected Guillaume and I in the first place was the idea of homophily and trying to say, do more similar objects tend to connect to each other? And we were using it in the context of substitutability of areas for housing and people choosing houses and so on. And so you can get the idea of, well, if two areas have similar types of schools, if they have similar connections to transport links and so on, then they should have connections in terms of being substitutable, there's another word I can't say, substitutable for dwellings, basically, when people are buying. And so you can measure this in these characteristics, and you also can include them in your models to say, okay, are you more likely to see connections between objects that have very similar characteristics, or is the opposite true? For example, if you're hooking up, you might see more heterosexual connections than homosexual connections. So in that case, you've got heterophily rather than homophily. I'll sort of skip ahead on that. So I will say there's a lot of material out there. There's some great tutorials if you just sort of Google statistical analysis of networks or social network analysis. There's some really nice material out there. If you know that Springer has free PDFs of their books. They have two very nice textbooks called Statistical Analysis of Network Data and Statistical Analysis of Network Data with R, which are really, really great resources if you're sort of working through this on your own. But better than that, there will be a one-day course featuring yours truly and co-starring Gwilym Price on the 28th of June, I think, is sort of, at the moment, the positive date. And so this is sort of, we'll be talking about it in R, but there are tons of other packages out there that are outside of R for visualizing this sort of network data and performing sort of summaries and so on. And that's it, basically. Thank you very much.